Hi everyone, and welcome to part 2 of a two-part video series on using the dynamic analysis modules in RFEM. In this video I will be picking up where I left off in part 1, where I previously showed how to enter the input data, and now we can run the calculations so we can view the linear time history analysis using time diagrams, again with the RF-DYNAM Pro-Forced Vibrations add-on module in RFEM. So all we need to do now is go back into the RF-DYNAM Pro add-on module and pick up where we left off in the first video, which is we have everything entered here within our input data. So all we need to do now is hit OK and calculate. So once the calculation is finished, you can see that right now we are under the RF-DYNAM Pro add-on module still and viewing our deformations within RFEM. What we can do is go to our tables down here and go to specifically table 5 dynamic analysis, and then under the drop down box here we want to select our dynamic load case 1, and then on the right hand side here we can check out our dynamic envelope, which is the worst case scenario from our analysis, but we can also take a look at the multiple timestamps that we have here as well. So now we're viewing our maximum deformations. So this is our results from our forced vibrations linear time history analysis, and from the machines that were placed at the top and the bottom section. And we can also show an animation of this deformation. So if I go up and click this button, right now it is pretty slow because it's going at each time step, but you can see how those deformations are happening over a period of time. Next thing we want to do is show the time course monitor. So that's down here in the tables, so we can click on this button, time history analysis. And what this will do is we'll pop up a new window, and right now we're not showing any function, but if we did show a function here, it would be over time, and we can select any possible object within our member, within our model. So what we want to do is we want to show the node at the point that is at the highest deformation, so that will be basically right next to our location of our machine here. So we'll click on that, and then you'll see that we're showing the displacement and the x direction. So you can see our displacement is shown over time, and this is given to us in inches. And you can see the maximum displacement is 2.124 inches. But really we're less interested in the displacement and really more interested in the acceleration in the x direction. So if I go here to value and I click on acceleration in x, now you can see we're looking at the graph here, and you should be able to see this is a good example of resonance. So our acceleration is starting at 0 and is increasing and increasing, and this would basically go on forever if it wasn't for the damping coefficients that we placed. And you can see that our maximum acceleration in the x direction is about 200 feet per second squared. And for those of you who don't know or might need a refresher, resonance is when two vibrations or frequencies share the same period. And when this happens, these vibrations will be amplified and can cause high accelerations and in turn high forces on your structure. So basically right now the frequency of our machines here is matching the maximum frequency that we saw in our natural vibrations case. So if we go back to our natural vibrations and we scroll all the way down to our natural frequency of 5.892, this is matching up with the frequency of our machines. So when the machine frequency matches up with the natural frequency of the structure, then this is what causes resonance. So basically what we want to do is get a different natural frequency of our structure, and to do this all we need to do is change the stiffness of our structure, and we can do that by changing maybe the cross sections of our columns here. So I will just turn the structure here and I will select our columns, and I will shrink these to something smaller to change the stiffness. So we can double click on them, go in and edit them, and up here we can then select our cross sections. So let's select something smaller, like a W6 by 25. And we'll click OK and click OK again. We'll have to clear our results. And now we can go up here and we can run our results again by going to calculate all. So now that all of our results have ran, we can go back into our table 5 here and go back to our dynamic envelope from our dynamic load case calculation. And we can click and look at our time course history monitor again. We want to view the node that's right next to our machine, and then we want to see the acceleration, and then we can click on our node graphically. And now you can see that we are no longer seeing resonance anymore, so our max acceleration is now only 20 feet per second squared, and you can see that we are no longer seeing that divergence of acceleration, and you can see we're at a stable acceleration for the course of time here in 15 seconds. So now this is where the video tutorial comes to an end, and hopefully you learned a lot throughout these two videos on how to perform a linear time history analysis on a structure, and I thank you for watching.